Hello again, and we will continue with our busy beaver function. As you will recall, we were looking at Turing machines which wrote stuff onto the tape, and they made strings of eyes, and busy beaver refers to moving back and forth and see how many eyes you could get onto the tape with a certain number of states. And what we've seen before, so that's our Turing machines, and what we've seen before is that it's a well-defined function, that for a given number of states, if I say, you have 5 states to play with, then there's only so many, 5 times 3 rules in each Turing machine. You can write each one so many ways. So there are only so many machines of a certain size. Each of them, when given a particular input tape, like a blank tape, will behave in a very deterministic way. And some of them will halt, and they might leave a unary number on the tape. And we're asking, of the machines which leave a unary number on the tape, which of these machines, what's the biggest unary number you can make out of a blank tape? So that's the busy beaver function. And as a practical matter, we were able to show that with n states, you could put n items onto the tape. You could write the unary number n on the tape. Just write the I, move, and change state. And we saw that. So that's like a really dumb, easy way to use n states. There might be cleverer ways. So if I gave you like 10 states, you could easily put 10 out there, but the most clever machine, the B of n machine, is probably a lot bigger. So what I want to do now is I want to show you as an inequality. So this is the line which basically shows you that B of n has to be, let me get this in here, has to be greater than or equal to, greater than or equal to n. So the B function is above this line, right? B of n, B of 10 is going to be greater than 10, all right? So that's a line with a slope of 1. But then we did a little better. We showed you, if you'll recall, back to our Turing machines, I had a little doubling machine over here which had 3 states. So we could put n things onto, n eyes onto the tape with n states. And then at the end of that, we could then go start the doubling process. And that doubled the eyes. Okay? And that's what we saw in the actual Turing machine a moment ago. This simulator. It started, it put 3 eyes on the tape, and then it doubled it. Okay. So from that we saw that with n states we could, n plus 3 states, if I had 3, and with 6 states I could double something. If I had 10 states, I could use 7 of them to write eyes and then 3 more to double it to make 14. So that should give us an improvement. I mean, that gives us a nicer inequality here. Essentially, it says that the B function is going to be above a line with slope 2 and an intercept of, on the x-axis here, of 3 over here. The intercept is going to be down here. So why don't I draw that for you briefly, roughly speaking. So that is going to be with that, okay, that line there, which we'll say has a slope of 2, we have to be greater than that, okay? Greater than or equal to 2n. So B is in this range above this line here. Okay, and that's pretty uncontroversial. And now I'm going to try and come up, look at a little bit more. And the first thing we're going to notice is that B of n, if B of n is greater than, or let's say B of x is greater than B of y, then x is greater than y. So basically this is saying that the function is monotone, non-decreasing. So we could say, to be strict, we could say greater than or equal to. So how do we know this? How do I know? Well, the point is that, going back to looking at our Turing machines here, if I said that I had a machine that had more states in it, all right, and I made the claim that the B function didn't go up or the B function went down, okay, so this is like suppose I claimed that this was happened to be my B function for my B machine for 6 states. Right, suppose I claimed that this is the best I could do with 6 states. And then somebody said, well, you can't do any better with 7 states. And I'd say, nonsense. I'll take my 6-state machine, I'll put in a new state, okay, 7, all right, and it'll do something, all right, let's just say it moves, it sees an I, and then it writes an I and moves left, and all right, so it just, wherever it is, it moves left until it gets to a blank. So state 7 gets to a blank, it'll write an I, and then not move and halt. And I'll change this guy to go to state 7. Okay. So if I claim that this is the best 6-state machine, okay, and the state 7 machines can't do any better, I'll just add an extra state. More states necessarily mean you got to do better, or you certainly can't do worse. So the B function increases. All right. The worst case I could do is just add another state which doesn't do anything. The B function non-decreasing. And there's no way out of that. All right. If I had an 8-state machine, and you claim that the B for the 7-state guy is a bigger number than for the 8-state guy, I'll just add a state which maybe never even reaches. So here's an 8-state machine which has the 7-state thing inside of it, and it never reaches the 8th-state. That's fine, it's an 8-state machine. Okay, so what this is saying is that if I say B of x is bigger than B of y, then x was more states. Alternatively, if you have more states, you have bigger output. So this is saying that B is monotone increasing. So this should be fairly uncontroversial. The next claim I'm going to make, the next inequality, is I'm going to say assume I can compute Bn, okay. The Turing machine takes n, okay, on the input tape, unary number, and halts with the number, okay. I'm using capital N here, but I still think we're confused here. Okay, this is similar to double machine. Okay, exactly analogous to the double machine, except instead of computing y equals 2x, it's computing y equals b of x. Okay, so this machine is a Turing machine. It has some number of states. We'll call it k states. All right. All right, so what? Well, let's just go back to here. And here is, we'll get rid of these for the moment. Okay. And if you'll recall in an earlier lecture, we did this thing of putting some number of i's on the tape and then running the doubler, right? And this gave us our inequality that n, this is n states to put I on the tape, put n on the tape. And over here it was 3 more states. So over here, okay, over here, tape contains 2n, right? Okay, so we used, okay, we used n plus 3 states used. Okay, so, and then we did the same thing. We tried doubling it again, right? Okay, 3 more states to double. And now down here, tape contains okay, so we could call this double, okay, this function here. Okay, so we have the same picture here. I could use n states to put some number on the tape. If I wanted to compute b of 10, I would put 10 onto the tape. Tape contains n. That's 10 states. Now we have k more states to compute b of n. Now the tape contains b of n. With n plus k states used. All right, that's not controversial. It's just like double. 3 more states to compute b of n again. B function. Okay, and now it's going to contain b of n. Okay, so instead of using n plus 6 states to double of double, we're going to use n plus 2k states to b of b. So, using n plus 2k states, we were able to put the number n on the tape, compute b with k states, take that output, put it back into the b function again, and it's another copy. It's another copy of the b machine here. Okay, and now this was k more states we now have B of B of n. Okay. N plus 2k states. K states. Okay. So the most productive gives at least okay, and we have an inequality B of B greater or equal to, okay, wait a second, B of n plus 2k, I got this right now, is greater than or equal to B of n plus 2k. I'm sorry, I'm screwed where we are. So with n plus 2k states, we managed to get B of n onto the machine. So we might have 10 states, and then k states to compute it, and then another k states, and we end up with B of 10. So the best, most clever n plus 2k state machine has to be at least that. Okay? Just like the best n plus 3 state machine had to be better than just doubling it. Okay. However, we have now walked off a cliff. And here's the problem. Here's x, here's y. So B of x is greater than or equal to B of y, then x is greater than y. Let's draw that inequality. This is a line, n plus 2k. All right? So the slope is 1, and the intercept is 2k. And okay, B of n is below that line. Here B of n is greater than 2n. Here it's a line with a slope of 2. Here it's below a line with a slope of 1. This is a contradiction. It's not possible for it simultaneously to be above a line with a slope of 2 and below a line with a slope of 1. Even if we fiddle with the intercepts, the slopes are going to kill us. This guy's going up faster than that guy is going up. Okay, what did we do wrong? Well, everything we've done is completely rigorous except for the point where I said, assume I could compute this function. If I could compute it, then I can write a program for it. That program has k states, and all the rest follows. I didn't say assume I could double it. I showed you a doubling machine, right? We can do arithmetic with computers, with Turing machines. But this function, it's not meaningful to say, I could write a program for it, but the program doesn't have a particular number of lines. The program has some number of lines. The program in Turing machine language has some number of states. If you can write that program, it has some number of states, and from that, all of this follows by construction. So we have a major contradiction here. So B, that busy beaver function, you give it a number in, there is a number out. If I said 38, then there's so many 38 state machines. I could, in theory, test all of those very large number of 38 state machines. Each of them has a behavior. Some don't halt, they go into infinite loops. Others put CRUD on the tape. Some of them leave a unary number of the tape. There is somewhere a most productive 38 state machine, and that's the value of B of n. So B of n is a well-defined function with a value, and I have shown that I don't have a good way to compute it, because the program, the existence of the program to compute it, ends up producing a contradiction. All right, so that's unfortunate, but this is like finding, some of the dark matter in the universe, because those functions that you can't compute are hard to find. They're there, you can find their existence, but actually locating such a function and being able to put your finger on it and say, this is a concretely defined function, it is defined everywhere on the number line, and it's not possible to write something to compute it. You're essentially proving a negative. So you end up proving a negative by things like contradiction. But there we have it. So thank you.